So Gaussian mixture models are very popular. They're a universal approximation to any smooth density, so that's great. But more importantly, you can actually fit parameters of Gaussian mixtures to data fairly efficiently, often using k-means as a starting point. So, practically speaking, they're very useful as a form of getting to understand the structure of the data. So let's start with an example. I'll just put down a bunch of data points and to say why would Gaussian mixtures work in this context, right? I'm just putting them down kind of randomly right now, making them up as I go. So if you were to think of these data points as being generated by this is in 2D, some two-dimensional density, obviously you cannot fit a single Gaussian very well to it, because typically there would be some sort of symmetry around a mean point that is lacking here. But you can see that I can think of this as potentially being generated from one Gaussian density, which is looks like it's fairly symmetric. These set of points could be thought of as coming from another Gaussian density, and perhaps these come from another, right? So it seems plausible that a mixture of three Gaussians could explain this data, that it could be sort of the source of the data, that kind of thing. Of course, you can see that the number of points is different for these three sort of clusters. So you would model these as you might think of this as a Gaussian coming from a Gaussian density with mean M1 and covariance C1. So this might be your M1 if you estimate it that way. This might be M2, N of X, M2, C2, and C2 would not be spherical. It basically has a major axis and a minor axis, so different eigenvalues along the different eigen directions. This one could be yet another one, M3, and this is N of X given M3, C3. This one again looks somewhat spherical, and also I'm drawing fewer points from the first and the third than from the second. So if you were explaining this data, we would associate the probabilities for each of these components as pi1, pi2, and pi3. And so basically, in order to fit, say, a three-component Gaussian mixture to this set of data points, we would need to specify pi1, pi2, pi3. Of course, these have to add up to 1. So I really am specifying only two parameters, that, and of course all the MK, CK, all the means and covariances for the three components, right? So in order to fit this data to a three-component Gaussian mixture, this is the set of parameter, it's a vector parameter that I want to estimate. And so the way we set it up is I have the data as usual. Let me change pen color. I have the data as usual, x1, x2 through xn. And I have these parameters theta that I want to estimate from the data. I have some hypothesis for how this, or a model for how this parameter influences the density. That's the parametric description that I have. And typically, I will assume that the data points, I always assume pretty much in that these data points are conditionally independent. So basically they are these n draws from this distribution. And changing pen color again, given the data points, maximum likelihood estimate of theta is just maximize this over theta, right? That's how we fit a Gaussian mixture model or any model to the data. One very popular way of fitting it is ML, right? And again, because I have this independence, so the condition, the density of the data decomposes into this product across the data points. It's natural to take the log, and so typically we would define the ML estimate as arg max over theta of, I would say, the log of the data point's likelihood. And of course, under our assumption or model of how the data points are generated, this is just the sum of these guys. So that's what a typical ML estimation problem look like. Now, for a Gaussian mixture, the conditional density of a typical data point is, of course, suppose I have k mixture components, big K mixture components, then the density looks like the probability of drawing that component, and then the density given that I have drawn the component, which is a standard Gaussian density. And when I take the log of that, it's a log of the sum, pi k n of x parameterized by mkck, right? So it's the log of a sum is not particularly nice. Nothing really good is going to come of it. So what we are saying is that a generic term like this in the summation looks like this, and it's not nice. It's actually unclear how I would actually optimize this sum of terms like these over all these parameters pi k, mk, and ck. So a direct maximum likelihood estimation is intractable here. So on the other hand, estimating the parameters of data that we know is drawn from a single Gaussian distribution is easy. So for example, if you told me that x1 through xn all come from a single Gaussian with a given mean and covariance, I know how to estimate them, and we'll talk about that in a minute. And so the procedure we use for dealing with a mixture of Gaussian is leverage ML estimation for a single Gaussian, and have an alternating procedure which is analogous to the alternating procedure in k-means, but a bit more sophisticated, and it turns out to be something that is a special case of the EM algorithm, the expectation maximization algorithm. So we'll first talk about the algorithm that comes out. We'll just sort of state the algorithm that comes out after talking about how to do ML estimation of mean and covariance for a single Gaussian, and then we'll talk in more detail about the EM algorithm and its generality, its convergence properties, and so on. Okay, so now let's talk about ML estimation for one Gaussian distribution. So what's our assumption? Our assumption here is that the data points x1 through xn are drawn from Gaussian distribution with unknown mean and covariance, and basically which means that for a generic data point, the density is this Gaussian density that we know as 1 over 2 pi to the dimension divided by 2, the determinant of the covariance to the power of half, and then the exponential, which is minus half x minus m transpose C inverse x minus m. Right, so that's the thing, and my parameter theta that I want to estimate is of course the mean vector and the covariance matrix, right? And what we of course deal with is because it's an exponential thing, it's natural for us to try to maximize the log of the likelihood function. So again, let's take a log of a generic of the density of a generic data point. That is going to be, let me get the exponential term first, minus half x minus m transpose C inverse x minus m, right? Minus d over 2 times log 2 pi minus half log of the determinant of C, right? And let me change pen color and say that, okay, well, this part I'm not interested in because it does not depend on the parameters of interest. And so what I want to maximize is the part that depends on M and C. And of course, I want to maximize the sum of the log likelihoods over the entire set of data points. So let me just say that I have this cost function that I want to maximize, which is summation I equals 1 to n over the data points of log of these individual likelihood functions, and that's minus half summation I equals 1 to n xi minus m transpose C inverse xi minus m for the ith data point, and then minus I'm summing that log determinant of C term over n of these guys, so minus n over 2 log of the determinant of C, right? So that's the thing. And actually, if you look at it as a function of m and C, these are actually the C as a function of C, it may or may not look that nice to you, but it's actually quite nice. And we'll talk about that in a moment. So let me first just write down the final answers before sketching the derivation. I won't have time to do any more than sketch. So the maximum likelihood estimates are as intuitive as you would expect. M hat is just directly the average of the data points, and C hat is just the covariance of the deviations of the data points from M hat, right? So that's our building block. That's what we'll use to go and handle the estimation of parameters for a Gaussian mixture model. Now we can talk briefly about how this comes about. If you look at the cost function that we are trying to optimize, it's a quadratic in M. So what I want is that the gradient of the cost function with respect to M is 0. I set it equal to 0, and I can see that in that cost function that these M appears 2 times, and so essentially and with the minus sign, so I'll basically get a minus half times minus 2 times, when I take out one of these M's, I basically get C inverse xi minus M summed over I, so minus half times is equal to 0. And we are assuming that we have a well-conditioned situation. I haven't chosen my parameters such that the C that I get will be non-invertible. So I can multiply both sides by C, and C inverse times C becomes identity, and what I get is summation I equals 1 to n xi minus m equals 0, which gives you that answer. That basically m is just a centroid of these points, of the data points. Regarding the optimization with respect to C, a full derivation would take us too far afield. Let me just provide a quick sketch. It's actually, if you're trying to find the maximizing C, instead, just for notation, it's simpler to maximize over the precision matrix. So basically, as long as it's an invertible transformation between these, optimizing C or optimizing P are the same thing. It just temporarily makes the notation easier. So I have the thing I want to optimize. Remember now that M is fixed, and I have to replace C inverse by P here. So xi minus M transpose C inverse, which is P, times xi minus M, and then minus half log det phi. Well, remember that the determinant of this is 1 over the determinant of the covariance. So basically the determinants are inverses of each other. So minus half log minus n over 2 log det C, that term here becomes plus n over 2 log of the determinant of P. And now I'm going to make sort of two statements. I have to basically set the gradient with respect to this to 0 in order to optimize over P. And I'm going to make two observations. One of them is simpler than the other. One is that if you give me a generic thing like X transpose P X, that's a real number. Remember, C inverse is in our particular case, it's a more special case also. But anyway, it doesn't matter here. If I look at this guy and I'm taking del P of this. Remember, P is a matrix, so del P, I'm taking the derivative with respect to each entry of the matrix, and so I'll get a matrix again. I can write it out as a matrix again, and that matrix is very easy to show, can be written as XX transpose, meaning to say del by del Pij of this guy. What is this guy? This is summation over I and j, xi Pij xj. So del by del, where is Pij operating? It's operating only on xi and xj. So the ijth entry of this gradient is just x, the outer product of x with itself. It's the xi xj. So that part, switching pen colors. This is what you use to handle the derivative of these terms. And the other one, I'm going to have to state, without proof, that del P of log of the determinant of P is just P inverse transpose. Remember, it again has to be a matrix of the same dimension as P. It's P inverse transpose, which in our case is C transpose. C is non-negative definite symmetric, so it's just C, right? So once you put those two things together, you get your answer. And this part requires a little more work, so I'm going to skip that.